Performance-based seismic evaluation of multi-story R.C.C building. Abstract from the recent earthquakes, it is noticed that the seismic risk in urban areas is increasing and the infrastructure facility is far from socioeconomically acceptable levels. Performance-based seismic design is an elastic design methodology done on the probable performance of the building under different ground motions. Thus the performance-based seismic design is a process that permits design of new buildings or upgrade of existing buildings with a realistic understanding of the risk of life, occupancy, and economic loss that may occur as a result of future earthquakes. Performance-based design begins with the selection of design criteria stated in the form of one or more performance objectives. In present study, an attempt is made to understand the procedure and methodology adopted in performance-based seismic evaluation of G+10, and G+20, Storey R.C.C building with and without shear wall. Nonlinear static pushover analysis is performed by using SAP 2000, a product of Computers and Structures International. The results of analysis have been compared in terms of base shear, story drift, story displacement and plastic hinge rotations, and found that both buildings satisfy strength as well as drift criteria. Keywords: performance-based seismic design, nonlinear static pushover analysis. Introduction. Earthquakes is one of the most devastating natural disasters that lead to catastrophic losses of lives and property around the world. According to the existing Standard Code of Practices, 1893, Part 1, 2002, more than 60% of existing land in India is susceptible to different kinds of earthquakes. Many existing structures are seismically deficient due to lack of awareness regarding seismic behavior of structures. Hence, we need to build structures that are capable to withstanding earthquakes with acceptable damage. The current seismic design codes in India and most of the other countries follow force-based design, FBD, method. Force-based approach does not give an idea about how a building will perform under seismic loading, whereas displacement-based approach is also known as performance-based seismic design, PBSD, evaluates how the building is going to perform under a given seismic loading. The concept of performance-based seismic engineering using nonlinear analysis to evaluate the behavior of a building. The most accurate nonlinear analysis is time history analysis, but it is very complex, requires many computations, time, and not practical for every design. So from a practical point of view, nonlinear static analysis, also known as pushover analysis, gives acceptable result. Pushover analysis is an incremental static analysis used to determine the force-displacement relationship, or the capacity curve, for a structural element. The analysis involves applying horizontal loads to a computer model of the structure incrementally, i.e. pushing the structure, and plotting the total applied shear force and associated lateral displacement at each increment, until the structure reaches a limit state of collapse condition. Methodology. Performance-based seismic evaluation of buildings is carried out using pushover analysis. It is a static nonlinear procedure in which the magnitude of the structural loading is incrementally increased. With the monotonic increase in the magnitude of the loading, weak links and the failure modes of the structure are found. As the load and displacement increases, the element, beams, columns, etc., begin to yield and deform inelastically. Pushover analysis requires capacity curve, demand curve, and performance objective. Capacity curve, which is roof displacement versus base shear graph, is obtained from the nonlinear static analysis. Capacity curve depends upon stiffness and deformation capacity of the structure. The demand curve is estimated by reducing 5% damp design spectrum by special reduction method. Capacity curve and demand curve is transformed into acceleration displacement response spectra, ADRs, which is acceleration versus displacement graph. The transformed capacity curve is called capacity spectrum. Capacity curve, demand curve, and ADRs is shown in Figure 1. Figure 1. Capacity curve, demand curve, and ADRs. The nonlinear properties in beams and columns have to be introduced for analysis, which can be introduced using predefined hinge properties in SAP 2000. The flexural default hinges, M3, to the beams at two ends was assigned. The interacting, PM2M3, frame hinges type a coupled hinge property was also assigned for all the columns at upper and lower ends. SAP 2000 take auto hinge property from ASCE 41-13 tables. All buildings are designed as per IS 456:2000, for adequate main and shear reinforcements, corresponding to the ultimate moment capacity level. Flexural plastic hinges will be developed along with the predicted values of ultimate moment capacity when there is no prior failure in shear. Therefore, there is no need for shear hinge modeling, as it is obvious for a code-designed building to fail in flexure and not in shear. Two pushover loads, push X and push Y, were defined as displacement controlled. The maximum target displacement of the structure was kept at 4% of the height of the building. Both pushover loads were run from final conditions of dead load. Description of analyzed buildings. In this paper, G+10 and G+20 stories buildings are preliminary designed by SAP 2000 v.19 for seismic zone. V buildings were designed as special moment resisting frame, SMRF, as per IS 1893-2002. Plan dimensions of buildings kept as 20m×15m with 5 bays in X direction and 3 bays in Y direction, Figure 2. Figure 2. Plan of building. Story height for ground floor is kept as 3.5 m and typical story height is kept uniform for all stories, i.e. 3 m. Slab thickness is kept 125 mm for all floors. Shear wall is modeled as mid-pier frame element. Thickness of shear wall is taken equal to 200 mm. As the building is symmetric, shear wall is provided in central bay of longer side of building frame. M25 grade of concrete and Fe415 grade of steel are used in all members. Loads considered. Following loads are considered for analysis of all buildings. Live load, 3.5 kN/m2 on all floors. As per IS 875, Part 2. Dead load, 3 kN/m2 on all floors and 16.8 kN/m wall load on all beams. Earthquake load, as per IS 1893:2002, PART1. Type of soil, medium soil, type 2, as per IS 1893, 2002, importance factor, I1. The time period for both buildings is program calculated as per IS 1893, 2002, was used to calculate the earthquake force for both buildings. For earthquake force analysis in SAP 2000, following loads were considered in the mass source, dead load plus times live load. The building is designed according to IS 456:2000 using SAP 2000 v.19, considering live load, dead load, and earthquake load in both directions X and Y with minimum eccentricity. The dimensions of beams and columns and designed reinforcement details of columns are mentioned in Table 1 and Table 2. Columns A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, C4, D1, D2, D3, D4, E1, E2, E3, E4, and F1, F2, F3, F4 can be identified from Figure 2. Results and discussion. The seismic performance of a building is evaluated in terms of capacity curve, performance point, and plastic hinge formation and story drift. Capacity curve. Pushover analysis gives an idea of the maximum base shear that the structure can resist at the time of the seismic load. For regular buildings, it can also give a rough idea about the global stiffness of the building. Capacity curve obtained after pushover analysis is plotted in Figure 3 and Figure 4. It is observed that buildings with shear wall is capable to resist larger base shear as compared to bare frame buildings. Maximum displacement was also observed in bare frame building. A table of hinge status at the ultimate stage is shown in Table 3. It was observed that in G+10 building without shear wall 74 hinges are formed between immediate occupancy and life safety range, and 228 hinges are formed beyond collapse range, by addition of shear wall only 18 hinges are formed between immediate occupancy and life safety range. So there is considerable decrease in hinge formation by addition of shear wall, and building lies between immediate occupancy and life safety range. Operational level, IO, immediate occupancy level, LS, life safety level, CP, collapse prevention level. In G+20, building without shear wall, 96 hinges are formed between immediate occupancy and life safety range, and 424 hinges are formed beyond collapse prevention state, but with shear wall addition hinges are not formed beyond immediate occupancy state. Building lies at immediate occupancy state, thus both buildings performed well up to design seismic load, and it can be easily said that performance of high-rise building is more affected than medium-rise building with addition of shear wall. Capacity demand spectrum. Capacity demand spectrum is the representation of structure's ability to resist the seismic demand. The point of intersection of capacity spectrum and demand spectrum is required performance point. Figure 7 and 8 shows the capacity spectrum curve as per ATC 40 of G+10 and G+20 buildings with shear wall respectively. Table 4 shows the performance point in terms of different structural parameter like base shear, V, displacement, D, spectral acceleration, SA, spectral displacement, SD, effective time period, TEF, effective damping, EFF. Storey drift of G+10 and G+20 Storey buildings for push X case with and without shear wall designed for dead load, live load, and the earthquake load is presented in figure 9 and 10. All buildings satisfy the strength requirements as well as satisfy inter-story drift criteria. As per 1893, 2002 clause no 7.11.1 maximum permissible inter-story drift is 0.004 times the story height. Conclusions. In this work, G+10 and G+20 stories buildings with and without shear wall have been taken for their seismic performance evaluation. Both buildings were designed for seismic zone V of India as per IS 1839:2002 and IS 456:2000. Pushover analysis of buildings was carried out using SAP 2000 Nonlinear software tool. Based on the present study, the following conclusion can be drawn. From pushover analysis it is seen that capacity of structure increases with the introduction of shear walls in both G10 and G20 buildings. There is a considerable reduction in hinge formation between immediate occupancy and life safety range, and no hinge formation above life safety range with addition of shear wall. As per IS 1893-2002 allowable story drift requirement is 0.004 times story height, which is satisfied by both G10 and G20 buildings. It is concluded that pushover analysis gives a better view of building performance under seismic load and its failure mechanism.